All right, today is part 2 for 3-5, which was on continuity and end behavior. So yesterday we talked about, or in part 1, we talked about continuity being continuous. Today we're going to talk about other things that are really important to look at when you look at a graph. First of all, we're going to talk about where is the graph increasing or decreasing, and then second of all, we're going to look at the end behavior of the graph, what's happening at the ends of the graph. So we're going to start with increasing and decreasing and constant. So those three ideas. They give you a really kind of complicated definition of this, but basically increasing means as you look left to right. So really important when we read our graphs, we have to go left to right. When we look at those, if the values for y, the function values, are getting bigger and bigger, that's increasing. If the values are getting smaller and smaller, then they are decreasing. And if they're staying the same, if the function values are always equal, then that would be a constant. So you kind of have those three different things. So we talk about a graph being either increasing, decreasing, or constant. So those are sort of your three options. So what we're going to do today is we're going to look at some graphs first and talk about what intervals of the domain are they increasing, decreasing, or remaining constant. So let's take a look at the first one. I think you recognize the parent graph. It's a parabola, and it is opening down because of the negative, and it's right 5 and then up 3. So if you want to go ahead and graph it on your calculator, you can pause the video, go ahead and get a graph on there so you can look at what's happening. And I'm just going to go ahead and make a sketch on my notes here so I have it ready to go. So we have 5, 3 is the vertex, and it's opening down. Just a rough sketch so we have the picture. All right, so when you look at this graph, the graph as we go left to right, it starts off and it is most definitely increasing till we get to that vertex point, and then it changes direction, and then it is decreasing after that. So you really have to make sure you read left to right. If you read it in the other direction, it's going to do different things. So we all want to read it the same way. So when I describe that then, I would say that this graph is increasing starting at, I'm going to use intervals here. So if we go left to right, we'll start at negative infinity always then for that first interval. From negative infinity all the way up to an x value always of 5, that graph was increasing. When we got to the vertex though, vertex really important point on a parabola, that's where it changes direction. So then from that point on, it's decreasing. So it's decreasing starting at 5 all the way to infinity and beyond, just like Buzz Lightyear. So it keeps going forever, and it's going to keep getting decreasing and decreasing as it goes to the right, starting at 5. So it's increasing from negative infinity to 5, and then it decreases from 5 to infinity. Now, at that point 5, so some people talk about, should we put a bracket? Is it included in either of those intervals? People argue kind of both ways. I think it's fine leaving it off. Technically, at the top point, it's not increasing or decreasing. That's where it's changing direction. So it's fine just to leave those as parentheses. But where one interval stops, the next one does need to start. So if it goes to 5, then the next one starts at 5. So always read your graph left to right. All right, let's take a look at a couple more quick ones of that. So again, hopefully you recognize the parent graph. Go ahead and make a sketch in your notes of what that looks like. So if you know what it does, great. Otherwise, graph it on your calculator just to reinforce what you know, and then make a sketch. So go ahead, pause the video so you can make that sketch. All right, so what happened to this graph? So it looks like we went left 3 and down 5 for our vertex, and then it is flatter. So again, super rough sketch here. So the 1/2, that was a vertical compression. So we're changing direction here at this vertex location, which is at -3, -5. Okay, so what happens to our graph? Well, prior to that, as we go left to right, the graph is decreasing. So it's decreasing here, and then we change direction at the vertex, and then it is increasing. So we always want to read left to right. So again, we're just going to describe what's happening. It's decreasing from negative infinity all the way up to the x value, which is at -3. And then at that point, that vertex, then it switches over to increasing. So it's increasing from -3 to infinity. So the more graphs change direction, the more we're going to have to take care of where those locations are. For some of our parent graphs, that's pretty straightforward. So do you think graphs always have to change direction? So when we think about what's happening in a graph, think of, just as a kind of an aside here to think about this, if you have a graph like x cubed, when you look at a graph like x cubed, that graph is always increasing as you go left to right. So this is increasing for all values of x. So from negative infinity to infinity, that graph continues to get bigger and bigger. So graphs don't have to change direction, but often they do. So let's talk about one that often does. Go ahead and get this one graphed on your calculator. So if you want to pause and go ahead and get that typed in, Okay, so I have mine graphed. Now you may be running into the same issue that I have. I can't really see where it's changing direction because it's off the top. So you may have to do some window adjustments sometimes when you do this. So I think if I've messed around with this enough, I think 25 for the Y max should be great, and then we can see the top of where it's changing direction. Okay, so let's talk about what the graph is doing as you go left to right. So it looks like the graph starts off increasing, and then it decreases, and then it increases again. So trying to keep some color coding here. So there's really three intervals of this graph. So we have an increasing, a decreasing, and an increasing. So I'm going to go ahead and just kind of articulate that here. So it's increasing from somewhere to somewhere, and then it's decreasing from somewhere to somewhere, and then it is increasing from somewhere to somewhere. All right, so let's see if we can figure out where those somewheres are. So when we look back at our graph, from negative infinity to whatever this x value is up here for this point, that would be where it's increasing. So we kind of have to eyeball it. It looks to me like it's at -2. What would be some places on our graphing calculator, though, that we could look to be able to see that? Well, what if I just trace? So I'm going to go ahead and trace and use my blinky cursor here, and I'm going to get it close. It's not going to be perfect, but when I get pretty close to -2, that looks like it's reaching its maximum if you look at what the y values are doing. Otherwise, you can also look at your table. Sorry, my graph in between there. But it sure looks like if I arrow back to like -2, it looks like that's the maximum value as well. So I'm not going to give you ones right now that aren't whole numbers. So I'm going to assume that that is changing direction at -2. So that means it's increasing from negative infinity to -2. Remember, we're reading left to right. All right, and then let's go back to the graph, and then it looks like it's going to be decreasing all the way to here, which I'm thinking is an x value, looks like of 1, and you can check that on tracing. So starting at -2 all the way to +1, it is decreasing. So remember, where one interval stops, the next one starts. Okay, so that must mean then starting at 1 to infinity, it must be increasing. So from 1 to infinity, it's increasing. So the more direction change you have, the more times you're going to have to look for those places. So those critical points where it changes direction, that's what we're going to talk about in 3.6, those max and min points. All right, so the last thing that we're going to talk about in 3.5 is something called end behavior. So end behavior for graph has to do with where those values are going, the y values, as x gets really, really big and really, really small. So at the ends of the graph. So we're going to use the same notation we did for the continuity test for this approaches idea. As it approaches something, we use an arrow. So x approaches infinity is how you'd read what I just wrote. And then as x approaches negative infinity means as x gets really, really small. What are the y values doing? Are they increasing? Are they decreasing? Are they becoming constant? We need to take a look at what those are. Okay, so we're going to talk about a couple of these very quickly. If you can please graph that 1 over x minus 2 on your calculator, just get that picture on there so we can talk about that. Basically, think about what the 1 over x graph looks like and what the -2 would do. If you subtract 2, what does that do to your graph? Well, the whole thing moves down to, I'm going to do a zoom 6 here so I get back to my regular window. So instead of having a horizontal asymptote at 0, this whole graph moved down 2. All right, so when we talk about end behavior, we're looking at two things. Y approaches what as x approaches infinity? So kind of leaving a blank there. And y approaches what as x approaches negative infinity. So as x gets big and small. So what do I mean by as x approaches infinity? So as x gets bigger and bigger and bigger and bigger, what is the y value approaching over there? Well, we know that the graph went down 2, right? So it looks like it's approaching -2. If you're not certain, trace on your graph or look at your table. When I go to my table, if I arrow and have x get bigger and bigger and bigger, look at what the y values are doing. As x gets larger, it sure looks like to me that the y's are getting closer and closer to -2. Your graphing calculator may never say -2, or if it does, it's only because it's rounding. But at some point, it's going to get closer and closer and closer to -2. That's where that asymptote went. So y approaches -2 as x gets really, really big. Okay, what happens in the other direction? Well, go back to your graph. That means going in this direction, looking that way. As x gets really, really small, what is y doing? Well, it's doing exactly the same thing. It's approaching that -2. And again, you can see that in your table. So I'm going to go to my table set and I'm going to start at 0 again. And then I'm going to arrow back. Okay, so as x gets smaller, It's coming from the other direction, but these values are getting closer and closer and closer again to -2. So as it gets smaller, it's going towards -2 as well, the function values are. So at both ends of this graph, it's getting closer to -2. If you understand what a parent graph looks like, you may not even have to graph these. So if you know that that's going to move that horizontal asymptote up and down, fantastic. Then you know exactly where that end behavior is going to go. All right, let's talk about some polynomial parent graphs here. X to the third, I think everybody's pretty familiar, pretty confident with what x to the third looks like. The 5 does what? Makes it skinnier, super rough sketch. But let's talk about what would happen here, end behavior. Y approaches what as x approaches infinity? And y approaches what as x approaches -infinity. All right, so when we take a look at this one, x approaches infinity means as you go this direction for x, what are the y's doing? And take a look at the graph. What does that arrow mean when you look at that? Well, it means it keeps getting bigger and bigger and bigger forever, right? Continues to grow. So as x gets bigger, so does the y. So y is approaching positive infinity. Go in the other direction. As x approaches -infinity, that means going this direction towards the left. What are the y's doing? What does that arrow mean? It means it continues to get smaller and smaller and smaller, or it approaches -infinity as y or as x approaches -infinity. So when you have an odd power, think about this for a second. The ends always go in the opposite direction, right? So if I had x to the 5th, it would do the same thing. X to the 7th, same thing. So odd powers, the ends always go in opposite directions. So positive infinity and -infinity for those y's. All right, so that highest degree term, super important. All right, so let's take a look at the next two. Now, you can type these into your calculator. You absolutely can, but I'm going to see if we can do this with just looking at that degree idea. What is the highest degree term in number 3? So circle that. All right, the highest degree one, since it's in descending order here, would be that one. So we know what 5x cubed looks like. We just talked about that one. But now, what does the negative do out front? Well, if you throw a negative out front, that reflects it over the x-axis. So ultimately, end behavior, I know there's going to be other twisted turns, but end behavior would do something like that. It's going to flip over the x-axis. All right, so when you write your end behavior statements, then y approaches what as x approaches infinity? Oops. And then y approaches what as x approaches -infinity? We know what's going to happen because we already know what the ends of those graphs are going to do. Let's make this look a little bit better for you. All right, so as x gets really, really big, as we go in this direction, now instead of going up, what is the y doing? Well, it's going down. It's approaching -infinity because we flipped. And then going the other direction, as x approaches -infinity, what is the y doing? Well, it's getting big. It's going to positive infinity. So if you reflect, the odd behavior is just going to flip. All right, let's take a look at the last one and then see if we can come up with some rules for these polynomials. What's the degree of number 4? Well, biggest degree term is x to the 4th, and think about what does x to the 4th normally do? Regular x to the 4th normally does this. Okay, when we throw a -6 out front, that means what's going to happen? Well, that graph is going to flip over the x-axis, so it's going to be opening down. So I know what the ends of those graphs are going to do. So y approaches what as x approaches infinity? Y approaches what as x approaches -infinity? Both ends do the same thing for even powers, right? Because the signs are always going to be the same. So in this situation, what are both ends of the graph doing? They're getting tiny. They're approaching -infinity. So if you have an even power, they always do the same thing. All right, so let's kind of wrap that up then. So for polynomials, even degree, they have the same end behavior. So they both go up or they both go down if it's reflected. Odd polynomials, they go in the opposite direction. So one's going up, the other one's going down. So this end behavior that I wrote out, this is if it's not reflected. This is what even and odd will always do at the ends. So for the odd ones, y is going up as x goes up, y goes down when x goes down. For evens, they go the same direction. But remember, if they're reflected, then they're going to do the exact opposite of that because they're going to flip. So we talked about increasing, decreasing, and end behavior.